Okay, we got it. Let's open up MATLAB and get started. All right, where were we? We did chapter 3, right? I believe we did. Let's take a look at our, it's always good to make sure we're in the right place here. MPCC Blackboard is where the homework is at. Log in here. Let's turn this on. All right, so weekly assignments. This is the 4th week, isn't it? 1, 2, 3, 4. Let's go to the week 4 assignment and see what it's all about. Yep. Yeah, so week 4 we should be into chapter 4, which is manipulating matrices, which is where we're at. So that's good. Week 3, under weekly assignments, should have been all the functions and the little built-in MATLAB stuff that we, all the different new functions we learned. So, we're in the right place. So I had a question from a student in the class. The question was about what we're supposed to turn in every week, so I'm going to reiterate that one last time. I'll probably reiterate it 1 or 2 more times before the class is over. But each week when you come to class or watch the video, either way, you should open up a file in MATLAB, an M file. So you go to MATLAB. You have an M file up here, and you should save it as with your name and the date. You should start with your name so that it doesn't start with a number, since M files have to start with a letter. And you can put in it class notes or whatever you want to. But that will be turned in Blackboard at the beginning of each assignment. As you go to the beginning of each assignment in Blackboard, for example, this week's assignment, week 4, the first problem says to submit an M file named, I tell you how to name it, week 4 underscore your name.m, and you'll have your code from taking notes in class. All the stuff that we do in class, you should be doing on your computer while we're doing it in class, and taking notes and making comments, putting comment lines in, and learning all that you can while we're doing this stuff in class. And then you just submit that file here so that I know that you were paying attention in class and following along in class. Then you go on and you do the homework problems here. Each one of those, each question in the homework problems may have several problems in it, may have just one problem in it, depends on the assignment. But you will submit M files for each one of those questions as well in the homework assignment. But also, in each week, you should jump on to our shared document here. And you should add to the shared document. Has anyone done this yet? We do have somebody on there. And you should put your name and the date and whatever it is. If it's a tip, if it's a shortcut, if it's a function that you learned about, some kind of trick in MATLAB, whatever it is, label it and tell us what it is. We've got several examples here, and then we've got our first for this year. Pressing Control-C stops MATLAB from computing if you made a command that outputs a lot of data or makes some kind of loop. So essentially, if MATLAB gets stuck you can press Control C, which cuts the loop and stops it. And so it'll let you start working again. Very useful little tool. Make sure that you're reading what other people write so that you don't repeat what they write. If you repeat what they write, you won't get credit for it. Now remember, you need to have one of these for each week of the class. We're in week 4, so everyone needs to have 4 at this point. I don't care if the dates are not exact. Right now we have February 2nd here. You should not put anything before that. You should date it on the date that you do it. But at this point, each person should have 4. So start looking for more of these. We need to have 12 per person by the time we're done. So this document should be pretty full when we're done. And it can be a very useful document. I wouldn't discourage you from printing it off and having it next to your desk when you're working next to your computer, when you're working on MATLAB every week. You'll find a lot of good stuff from your fellow students here. But those are the 3 things. The shared document, the homework assignment, which has 2 different things in it. The homework assignment, which has your notes from class in the first question, and then in subsequent questions there are problems that you need to complete and turn in in M-Files. Any questions on what we're doing each week for this class? And that's how we'll do everything until we get to the final project. When we get to the final project, instead of having, we'll get to the final project at least 3 weeks before the end of class, which is why we only do 12 of these things. I think we have let's see. Yeah, there are 12 weekly assignments, so we're only entering 12 things in the shared document. But for those last 3-4 weeks of class, if you include finals week, that last almost month of class is going to be the final project, where I will give you specific things that I want you to complete in a particular week, depending on the project, and you will turn in your program to that point, hopefully having taken care of what you're supposed to take care of that week for that program. So, any questions? Concerns? Okay. Excuse me. So let's get started with this week. We're in chapter 4, and we are going to cover, I think we're covering all of chapter 4 this week. Let's see what we're doing in week 5 really quick to make sure. The reason I'm not sure is because they changed the book format a little bit, so I just need to make sure that we're not doing anything funky. No, chapter 5 is next week, so we're done with chapter 4 in 1 week. So we got to cover it all today. Shouldn't be too difficult. So let's get on with it. Chapter 4. Chapter 4 is all about manipulating matrices in MATLAB. Matrices, of course, is the plural form of matrix. And we're going to learn how to create different types of matrices, pull things out of matrices, put things into matrices, combine matrices, separate a matrix into multiple matrices. We're going to learn how to do all kinds of things like this. Again, this is still very much, we're not really doing any problem solving at this point. We're still just doing nuts and bolts. We're still learning how to use MATLAB to do things so that we can solve problems. So we're still kind of building our toolbox. But let's go ahead and start. We've already talked about how we can build a different matrix, but let's review it really quick. Let's start off with just a very simple matrix A. They say that A equals, and we're going to use square brackets to tell MATLAB that it's a matrix. I'm going to use a semicolon to suppress my output. Actually, no, I won't. Yeah, I will. And I'm going to just make a simple matrix. This is actually a matrix, 3.5. That's the first matrix they do in chapter 4 here. And it is a matrix, even though it's just a single number. It doesn't matter if it's a single number, it's still considered a matrix in MATLAB. Or you can make multiple matrices, or matrices with multiple multiple elements. Each separate thing inside of a matrix is called an element. And so this particular one, 1.5 space 3.1, is also, it can also be expressed a different way. If we go ahead and press enter on this, we see that it's got a single row and 2 columns. But we could also say that B is equal to 1.5 comma 3.1, and that will give us the same matrix, a single row and 2 columns. Now if we want, instead of a single row, 2 columns, we want a single column and 2 rows, then we need to separate the columns somehow. Separate the rows somehow. And the way that we do that is use a semicolon inside of here. So we have our semicolon, 3.1. Now a lot of people will write their matrix like this, where they don't have space between the commas or spaces between the semicolons. I try to avoid that. I try to put spaces everywhere just because it's easier to read that way. Some people will even put spaces after their little square brackets. I don't like to do that. To me that looks a little bit, that's hard for me to read. I prefer this. This looks very clean to me. And this of course will give us a single column and 2 rows. So this is a 2 by 1, 2 rows, 1 column. Right? But you could also do this by doing B equals let's see if it'll let me do this here. I don't think it will actually. If I do B equals 1.5, yeah. If I do this in my M file though, if I do B equals 1.5, oh, let's try it down here again, because I think I can do it this way. B, if I do B equals, and I do my square brackets, and I only do the first square bracket, and I do 1.5, and then I do enter, then I can enter in the next row at 3.1 and then close the square brackets. And then it will let me do it that way. But if you close your square brackets before you do your next row, then you can't. So you can actually do it that way in your M file as well. I can do B equals 1.5, hit enter, and in an M file it'll actually take you down to a place that makes sense as far as formatting goes. So I can do 3.1, and I could even do more. I could do 5.6, and I could do another one, 7 and 3 and 4 and 2, and then close my square brackets, and it'll make a nice thing when I run this thing. So if I actually run this file, I get B equals 1.5, this single column but a whole bunch of rows, right? So this one happens to be 1, 2, 3, 4, 5, 6, 7 rows. So this would be a 7 row by 1 column matrix, or 7 by 1 matrix. So lots of different ways to enter in these simple matrices. And of course, if you're doing multiple columns and multiple rows, you can use the same concepts. So if we're going to do C equals, we'll do the one that's here in the book. We'll start off with our square bracket. And remember, rows can be, columns can be either separated by commas or spaces. And just for speed's sake, I'm just going to use spaces. So I'll do -1, do a space, do a 0, do a space, do a 0, and then I'll hit return. And I'll go ahead and I'm going to space over here so that it looks a little cleaner. And now for my second row, I'm going to do 1 space 0. And then for my third one, I'm going to come over here and I'm going to do 1 space -1 space 0. And then my fourth, I'm going to do 0 space 2. And then I go ahead and close that off, hit return, and I've got a nice little 4 by 3 matrix. Right? Probably the simplest way to enter these in the command window, and simplest and cleanest way to enter these into the command window, because what you enter in looks very similar to what it is actually going in. Right? Another way to very simply enter a matrix is to create a matrix. See, you could create it as just an open matrix like this, just an empty matrix, and then come over here and click on it, and then just start entering in numbers. You do 3, and then got to click on it first. Put in your number 2, and then you can either tab or use arrows up and down, or tab will just take you straight across. And you can start entering in things, 3, 4, 56, 70, through 2, whatever. You can just start building your matrix. And this is a very, very quick way to make a matrix, especially because if you start leaving spaces, see, if I leave a bunch of spaces here and then I put in a number here, it fills in zeros for me. So it completes the matrix for me. Come down here and I say, I have one number down here at column 10 and row 13, 78, but the rest are zeros. I can just fill that in and it'll fill in the rest zeros for me. And then if I just close out of this, it will create this huge matrix that would normally take a lot of time to enter in. But I just pounded in the numbers in that little spreadsheet that you have available to you. So lots of different ways to put in your numbers into a matrix and to build your matrix. Let's see here. Okay, so let's see here. Okay, so let's look at now creating a matrix from another matrix. Let's start off with, that's our matrix B really quick. I don't remember what it was here. That's our matrix B. Let's go back to what it was before. I think that we had B equal to 1.5 and 3.1. Right? So we have this matrix, very simple, single row, 2 columns. But let's say that we want to build a new matrix, and we'll call this new matrix S. And this new matrix is going to be really just an addition to B. We just want to put one more number in B. And let's say that number that we want to put in is 3, and we want to put it at the beginning of B. So we can actually just put in 3, comma, B, or 3 space B. We'll give you the same thing. And it will actually put a 3 at the beginning of the matrix B and add a new number into B. So you can do this with not only with adding numbers into a matrix, but you can add matrices together. So let's have the matrix D, not adding them together, but you can combine them together. So we have D, let's say D is equal to 4, 5, right? And now I want to make the matrix E, better not use E since it has a value in MATLAB, I think. No, I don't think it does actually. So if I use E is equal to the matrix B, goodness, B space D, then we make a new matrix that has those two, the elements of B and D in it, just like we put them in. Right? And we could actually turn them into columns if we wanted to, because remember we had this little function here that allowed us to flip a matrix, flip its rows and columns. So if we do B with a single quote mark next to it, or a prime, and then we do D with a little prime on it, then what it does is it takes B and it makes it instead of being 1 row and 2 columns, it becomes 2 rows and 1 column. And same with D, and then it makes a new matrix like this. So this one is B, this column over here is B turned on its head, and this one is D turned on its head. All right, we've made a new matrix. So you can do this, you can add on to the rows, you can also add on to the columns. If we did if we do a new matrix F, we could make a new matrix F that is equal to E, and then we can add a new column to it. But remember, when you put in a new column, you need to have semicolon, or well, in this case, you just need to have a semicolon because we're adding a complete. We've got two columns in E already, so we're going to add a semicolon. We're going to add in a new column here. And our new column is going to have to be entered in a column form, so that's going to be a little bit difficult for us. I'm trying to think how I'm going to do that for us here. Excuse me. What I'm going to have to do is I'll put in D and a D again. I'll put in another D column here. No, that didn't work. Why didn't it work? There we go. I actually put in another row is what I did. Okay, so I see what I did. So E is already the 1.53.145, and I added in a new row when I put in the semicolon. So if I wanted to put in a new column, I would have to put in a space, and then I would have to do this, and that would put in a new column, right? So you can essentially build onto these things. This is called concatenation. You actually saw the word up here in my thing right here, concatenating, right? When you're concatenating a matrix, you're adding more elements onto an existing matrix in some way or form. So, and you can do this in lots of different ways. We'll find many other ways to do this as well as we move through the class, which is very useful when you're doing algebra or any kind of mathematics with these huge blocks of numbers, as we will see as we move forward here. Let's take a look at so now let's actually now look at changing the elements in a matrix. So each of the an element of a matrix is just each separate member of it. It doesn't have to be a number, just so you know. Not all elements of matrices are always numbers. We can do different things with them. But each separate part that it has its own place in the matrix is called an element. And each one of those elements has an index. The index is its row and its column. So the index of this one right up here in the top left corner, the index is 1, 1. First row, first column. This one is 1, 2, then 1, 3, and so on and so forth. And yes, sir.
The notes. I know we have to take notes on here, but the notes I have on here are I couldn't transfer the notes from here to
Do you have a USB drive or an email account? Just email them to yourself.
Oh, okay. Come in this format?
Yeah. Yeah, you can email them to yourself. Sorry. So yeah, if you're working on one computer and you want to go to another computer to use MATLAB, you can easily just save the file or email the file to yourself. M files are very low memory. They don't take up any memory at all, hardly. They're just a text file. And when you open it up on another computer in MATLAB, you have to open it within MATLAB. Then yeah, everything will be transferred over. It'll just open like it normally would in MATLAB. No big deal. So anyway, we're at this point now where we're going to talk about how we can change an element in a matrix, because each element has this index. So since this previous matrix is called F, we can do F and then we do parentheses, and we can call out any one of the numbers. So if I call out 1, 1 and hit enter, it will tell me what is the matrix element F1, 1, or what's in the matrix F at row 1, column 1. It's pretty straightforward. If I call out F2 comma 3, sorry, F2 comma 3, what is it going to give me? Give me row 2, column 3. What's it going to give me? What's in row 2, column 3? There is no row 2, column 3, is it? Is there? So if you call for something that is not there, it's going to go outside the matrix and it'll say, sorry, you called for something not allowed. But if I do 2 comma 2, then it does give us 5, right? So you have to be aware of what size your matrix is and what you're asking for. But then if I change the matrix, then I can call for other things. But I can also ask for F2. What do you think that's going to give me? Let's find out. It gives me 3.1. What is that? Where is that? F2 is 3.1 apparently. So right there. If I ask for, let's ask for F3 and see what it gives me. F3 gives me 4. Let's ask what F5 gives me. The answer is 5, right there. What it does, if you ask for just a single index, is it goes down column by column and it gives every element in the matrix an index number. So the first one in the first column is 1, then 2, then 3, then 4 in the second column, 5, 6, and it just goes down the columns, and it gives everything a number all the way up to the last element. So you can call it from the first element to the last element, or you can call it by row and column. Okay? But there's also one other thing that you can do, and that is I can call for F1 and then put a little semicolon here. That semicolon means everything. So this is going to be F, and what is the first number, row or column? It's the row. So what this thing is saying is give me everything that's in row 1. So all the columns that are in row 1. So if I hit this one, it gives me the entire row 1. And if I do the other thing, if I do F, and I do everything, all the rows, in other words, in column 2, then it's going to give me everything in column 2. Okay? So you can separate out things from your matrix. You can call things out. You can call out individual elements by row and column. You can call out individual elements just by their order in the matrix. Or you can call out individual rows and individual columns. You can also do, let's make a bigger matrix here really quick. Let's see, what's our biggest matrix? We got this matrix C right here, which is really quite big. So let's do a matrix C. And let's call out everything from row 1 to row 3. And let's do all of the columns. See what that does for us. So that gives us all of rows 1 through 3. I could do the same thing for row 1 through row 7. Or I could do row 4 through 7 and all the columns. And it'll give me just that part of the matrix. I can also do all of the columns from 7 to 12. Oops. How big is the matrix again? 13 by 10, so I can only go up to 10, 7 to 10. So I can do all the columns from 7 to 10, and it'll give me all those columns instead, right? So those are what we call the colon operators with matrix when you're calling matrices. And what the colon means is all of. So if you put it between two numbers, it's all of the things between those two numbers. And if you just put in the colon, it means all of those rows or all of those columns. Okay? I've never tried this. Let's try this. C, let's just try and see if it'll give us all of C if we do this. It does. That's cool. So what we do, what I just did is I called for all of C just in order. So it gives me all the numbers that are in C in a single string of numbers. From the first one in the first column, the second one in the first column, the third one in the first column, all the way down to that whole column, and then it starts the next column, and then the next column, and the next column, and it goes through all the columns one by one and just writes them as a single column. I wonder what happens if I put a nope, well, let me do that. Try to do this, and then put this on the outside. Yeah, then it does it all in a big row. So you can do that. Interesting. Never done that before. So that is how you call things out of a matrix. Let's just take a chunk out of the matrix. So let's call for C, and let's take out rows 2 through 5, but only the columns. Let's see, is this how I want to do this? Yeah, but let's only take out certain columns. Let's only take out columns 6 through 9. So it just took a chunk out of the matrix of C. We knew that there was that big chunk that had zeros in it, so that's where we took it from. So all kinds of different ways you can pull stuff out of a matrix, and using either the row column indexing, using the single number indexing, using the colon operator in different ways to pull out different parts of the matrix, and very useful feature. So let's take a look at excuse me. Let's take a look at some data. I've got this data file somewhere. Let's see if I can find it. Asheville. Apparently I'm not connected to the internet. That would explain a lot. I'm supposed to be connected even if I'm not connected to the internet. Good night. Really? All right. Come on. Okay, let's see. I'm looking for a file. See if I can find it anywhere. Okay, I'm probably going to have to just download this really quick. Let's see. Pearson. All right. Sorry for the delay here. I thought I had that file somewhere, but apparently I don't. See if I can get in here really quick. You gotta be kidding me. Now I gotta look up my password for this. Oh, it's just a different. I see. Okay. Where'd it go? Oh, sorry. All right. So they give me this option for downloading these things, but now I can't find it. Here it is. We're in chapter 4. There's my Asheville. All right. This is what we want to open. Let's go find it. Well, let's actually just drag it over here. So whenever you have a file of data you need to download, you need to actually bring it into the folder that you're working in. Otherwise, it won't know what to do with it. I'm going to bring in these two, actually. I thought I was. I'll just use this one. So now I've got this data file. It's an Excel file, actually. And I'm going to import some data. I'm going to import Asheville XLS, open that up, and brings it in here, all the numbers, that's good, import selection, and we're good to go. It should be good. So now I can use that data. Okay, so now we're there, we're good. Yeah. Okay, so the first example we're going to do is on page 126, and it goes all the way through 128. And we're going to input a bunch of temperature data from this town called Asheville. I think it's in Tennessee. But the data is Asheville _1999.xls. And what they want us to do is they want us to input the data, import the data, and then they want us to make it into a matrix of data. And then, let's see, they want us to do what? Develop a hand example. What is the hand example they're talking about? They're going to do some averages, which we learned how to do in the last chapter. They're going to make a new table of averages, and they're going to take out the lowest temperatures, and they're going to find the lowest temperatures and the highest temperatures and take those out. They're going to do a lot of different things that we've learned how to do here. So what I'm going to do is I'm going to start off by clearing my screen here, clear my command window. I'm going to clear all my workspace, clear all my variables that I've got in there. Do a CLC here again. And then we're going to go ahead and start. So remember that we want to use some comment lines. So in my comment lines, I may tell you what example this is, what problem this is. This is example 4.1. And I might explain what we're going to do. And there might be a little bit of explaining to do, might be a lot of explaining to do. You might have a paragraph that explains what you're going to do. You might just have a sentence. You might just say, we are going to do some averages and highs and lows from a temperature file or something like that, right? You might give more or less depending on what you want to do. And then I'm going to go ahead and give myself a little space here. I want to make some space for myself. And I'm going to say what I'm going to do, what I'm going to start with. I'm going to start by loading my data file. Right? So that's the first thing I'm going to do. Load a data file. And the way we do this is we use the function load, and we type in the file that we're getting this from, load Asheville _99. Don't need to have anything else on there. The .xls is not necessary. It's 1999. There you go. I'm going to load this file, Asheville 1999. Now let's see what happens when we do that. It doesn't read it, no such file or directory. That's because it's not the, apparently it didn't do it when I said I should do it. Okay, so let's go back to Asheville here and let's import some data. And we're going to open this one. And let's go back up here to import data. There we go. Now it's in there. Let's close this again. Okay, unfortunately what it's done for us, if we open this up, it's imported each of the columns of the matrix separately. So we don't want to do that. Let's go back. Shoot, what did I just do? I just closed my MATLAB, dang it. Why did it let me do that? Come on now. Okay, so let's go back to Asheville here and let's go back to import data. Let's import this again, open. So what it did is it imported, apparently, column by column. And I don't want to do that because I chose the wrong thing up here. I either want to import a numeric matrix. I want to import each thing in the matrix. So then I'm going to go here and import this data. And it should bring it in now as one single 12 by 25 matrix, which is what I wanted. So now I've got it in there. And let's go back to where I was before. I did the clear, I did the close, I did the CLC, I did all that stuff. And then I did all my notes, and now I'm going to just load Asheville. _1999. All right, now let's see if it works. It still doesn't like it. Why not? It says it's in there. Oh, I guess I don't have to do it anymore because I got it out here already. So if you import the data this way, you don't have to do it. If we do it the other way that we would do it, where we would have to load it, and that's the one I'm trying to do here. So this is a new feature in MATLAB that I'm not familiar with. So the import data feature is a new feature. If you use the new feature of import data right now, then you actually get it loaded in as a variable and you don't have to load it in directly. If I want to load in something that is a file like ab.mat, for example, I could load that one, load ab, and it would load it in just like they automatically load it in Asheville. So it's kind of nice that they've built that in so we don't have to load it. So you can either do the import data and it automatically loads it, or you can load it directly from a MAT file. And that MAT file we do have, it's over here. We have the Asheville.mat file, so we could bring that over here, maybe. Let's see, where are we? Maybe it'll let me load it. No, apparently it won't. But anyway, if you copy that or you load that into there, then you would have to use the load function. Otherwise, you don't have to, which is kind of nice. Anyway, we've already got that in there, and now what we want to do is we want to get all the excuse me. We want to get the average mean temperatures for each month. Let's see, what did they say they want us to do? They want us to get the mean high temperatures from the matrix. Okay? Mean high temperatures. Well, it might be good for us to know what those are. So let's go to our Asheville file and figure out what this Asheville file is all about. So we look in here, and it looks like we've got months is our first column, it looks like. And then it looks like the high temperature is column 2, the low temperature is column 3, probably this column 4 here, or column D rather, is probably our average temperature. I don't know what all these other numbers are. We should figure those out, I guess. Did they tell us what those are in here? Mean, maximum, mean, minimum, highest temperature, and lowest temperature. So this is the high, this is the low, this is the, let's see. So that's the mean high, mean low. What is the highest temperature? I don't see the highest temperature anywhere. Maybe this one? Maybe this one? We should open this up in Excel and see if they tell us more information about this. Yeah, they don't have them labeled in here either, so we just kind of have to figure it out, I guess. In here, it's not even correct. That's kind of confusing. Why do they do that to us? This is the first time I've used this file, so you have to excuse me for trying to figure it out at the moment here. Well, it says here that let's actually just go off of there. We can actually figure out what they are from the code that they do in the book. It says if you're extracting the maximum temperature, you're taking it from this is what we're going to do here. Let me show you here. If we're going to get the mean high temperature, then we're going to use this this command. We'll call it the mean of the max, which is the mean of the high temperature, the average high temperature. Mean underscore, can't use a dash, it's not allowed. So we use mean underscore max, and we set that equal to our Asheville underscore 1999. But we're going to set it equal to specifically the first through the 12th rows, second column. Right? So the second column in this thing is supposedly all of our max stuff here. Why didn't it do that? It's all in there. Asheville 19. Oh, because it's capitalized. They capitalized it, so we have to capitalize it. Oops. Asheville. And they don't have an underscore in there. So you have to go by whatever the word is over here, I guess. So then if we take that, goodness gracious, what's going on here? Oh, I spelt it wrong again. Asheville, there we go. Okay, so then it pulls out the second column, which is all the average high temperatures. We do a very similar thing for the minimum. Instead of the mean maximum, we use mean minimum. We call it mean minimum. And instead of taking out the second column, we're going to take out, they say it's the third column. So there's our third column. Now we have actually extracted the second and third columns from our temperature file, and then we've made new matrices from them, 2 new matrices. And if you want to calculate the annual one, annual mean for the maximum temperature, which I'm just going to call annual mean, they use a longer thing, but I'm just going to call this. The annual mean is going to be the mean, let's see, the annual max, annual max will just be the mean underscore max matrix, but we're going to take the mean of it. We're going to take the average of it. Right? So if you take the average of that mean max thing, then it'll give you the average annual temperature at its maximum. Average maximum annual temperature. Do the same thing with minimum to calculate the annual minimum temperature for those 12 months, and you'll get the 46. And then it turns out it's the 8th column that tells you what the high temperature is. So if you make a thing here called high temperature for the year, then the high temperature for the year is going to equal Ash, you got to do capitals, Asheville 1999, and we want to take from 1 to 12, from rows 1 to 12 again, but we want to take the 8th column. That'll give us our maximums. Again, I spelled it wrong, so I spelled it right for me. So there's all my high temperatures from the year. And if I want to know my biggest temperature of the year, then I can take take the maximum of high temp. Right? It's called high underscore temp, not high dash temp. There we go. So the high temperature for the year is 96. If I wanted to take the average high temp, I could do that. The average high temp would be the mean of high temp. Right? There's your average high temperature for the year. And so on. And you can just do this again and again ad nauseum. There's so many different things you could do. Once you've got your all your averages here, we've got high temperatures and mean minimum temperatures, mean maximum temperatures. We could make a new average matrix. A new average matrix could look like this. It could look like mean underscore max, and then the next column, or the next column would be the next column would be mean underscore min, and then the next column would be high temp. So here you have all of your average lows, or average highs, average lows, and your high temperatures. Right? And you could do all kinds of things with the tools we've used so far. Rearranging and making new tables, and calculating new things from different matrices and so on and so forth. So, that takes us all the way through the first section. What time is it here? 1 o'clock. The next section is just examples. And then the last section in this chapter are special matrices. So what I'm going to do is I'm going to take a little bit of a break right now, maybe 10 minutes or so. I need a little extra long today. Take a little walk. Then we'll do some more examples from section 4.2, and then we'll save the very end of the class to look at some special types of matrices that maybe we will use, that we will definitely use. But so we'll take a little break here. Next 10 minutes or so.
We're getting further into that. We only did example problems from the 3 days we missed last week. Yeah, I tried Googling like how to do that was a easy function, and it popped up like that. Yeah, no, we didn't cover any of that. We only covered the example problems in the work. So that's kind of what shoots me off. Is, 'cause those are the brains.
It's like, yeah.
Yeah, cool, right? Yeah, dollar bill. The ground, right?
You know, like, no food emotions. Everything has like, you know, it's like, there's like market systems. I don't know. There's something I found on the page. Supply and it's like a banner. Seconds.
Yeah, I found like, no joke, like some like 8 things. Like, out of the entire year, you know, 8 pennies. Yeah, okay. Let's do that. Let's do this. Yeah, if you invest in stock, then it's like what, 2008, right? Economic crisis. Man, that is pretty scary. Like, even though it seems so severe, like, it seems like it's like slight check to the year. I mean, scary stuff, dude. I was looking at this, we did like a little stock thing in history, actually. And this like, anyway, it was like big stock or whatever. That kind of got me interested in looking at like real stocks. And I started looking at some stocks, and there's a stock, it's like an Australian company where like they make money. I don't know how I got there, but I was like, man, this is pretty cool stuff. Like, and it was like at least 4 years ago. And if I would have invested into it, oh my goodness, I would not want to do that. I mean, it went up. It was $2 when I first looked at it, and it went up to $10. Like, yeah, that's pretty big. But at the same time, it's like what you invest 5,000, you get like 40,000. Like, you know, it's not that much in the grand scheme of things. It is a lot, but it's not like, you know, it's not like you know investing into penny stocks and then like.
Well,
Yeah.
that's
But that's
a
like
lot.
insurance. Yeah, that's what I'm saying. I mean, it's still pretty cool to like see like. And now to this day, I'm like trying to invest it, and recently it's not over 10 to 15. Of course, it's kind of like, kind of going 15 to like 14 to 16. Oh, when I get invested in it, but I'll be saying that for years now. When it's 30. Should invest in it, man. Yeah, I was reading about their, it's like a pretty small company. It's literally $50. But like, I was reading how, freaking, how they were planning on doing business with like China and stuff, and like how they're doing, because that's it, it's like, they're a honey company, you know, they're like honey company. They're planning on like doing like more, I guess like herbal, antidote medicine in China. Like, so should we go to China? Yeah, we probably will be able to learn things. Here I am, thinking about investing.
Okay. Ah. Let's see what we can see here. CLC. So, section 4.2. Section 4.2. All right. Just a little review. If we have the matrix A, which is equal to this, it's they're doing 5, 10, 15, 20, 25, like that. And then you have another matrix Y, which equals oops. And then you try to multiply them. Let's see.
It doesn't need the brackets. Why?
It's not always necessary to do that. For just a single row, you don't necessarily have to put in the brackets. Well, not true. For a single, if you're using the colon notation, you don't have to use the brackets all the time. So, when you just use y, if you just use x equals 1:5, it automatically assumes you want a matrix of the numbers between 1 and 5 steps of 1, right? Whereas if you put a colon inside of a matrix, it does something different like we learned before. It does something slightly different. So anyway, we have this, and let's see, x and y, what is y? Let's make y equal to 5, right? So now y is 5 and x is 1, 2, 3, 4, 5. And you can do this math right here, that a equals x times y, which is actually what they were doing in the book. I'd skipped a page. And that gives you this, because whenever you have a matrix that is just a single 1 by 1 matrix, you go right up here and you can see that it's a 1 by 1 double. It's a scalar, and so you can multiply that scalar by any matrix. Any matrix can be multiplied by a scalar. However, you cannot just multiply any two matrices together. So if you have y equal to 1 to 3 like we had before, like this, and then you try to do a equals x times y, it won't let you do it because you can't just multiply any old matrix by any old matrix. We have two matrices. The matrices do not agree in their size. That's what that means when they say the inner matrix dimensions must agree. And that has something to do with matrix algebra, which we don't cover in this class. But one thing that you can know is that if you have two similar matrices that have the same number of rows and columns, so if you have y equals 1, 2, 3 and z equals from 4 to 6, so 4, 5, 6 in other words, right? Then you can multiply y and z. Let's see how we do it. B equals y times z. No, still doesn't let you do it. But if I do b equals y dot times z, then that's going to tell us that it wants you to multiply these together element by element. So the first element in the first row, first column, will be multiplied by the first element in the first column of A and B. So you can do this, and it'll just multiply them element by element. Okay, so you have to use that dot times in there. What's that? It has to do with how matrix math is done. I'm not going to give you the details on how matrix math is done, because it's a whole new class. You may have done it a little bit in an algebra class before, possibly, but if you have done it in an algebra class, you know what it means. You know that your rows, your columns have to match your rows if you're going to multiply A and B, right? And then you do that across the column, across the row, down the column, kind of multiplying. But if you haven't done that before, don't worry about it. We're not going to hold you to that. We're just telling you that multiplying matrices is different than multiplying numbers. So if you want to multiply element by element by element in a matrix, just multiply them like scalars, then you have to use that dot times. You can do the same thing when you do z and you raise it to a power of x, for example. Or raise it to y, rather. So if I raise z to the yth power, it doesn't let me do it there, but I can do it if I do the dot raised to the power. Then every element in z will be raised to the same element in y. Remember that y was 1, 2, 3, so we raised the first element in z, which was 4, to the 1th power, which is 4 to 1, which is just 4. Then we raised 5 to the 2nd power, which is 25. Then we raised 6 to the 3rd power, which is 36 times 6, which is 216. So we remember that is the case when you're dealing with matrices, and don't make the mistake of trying to multiply two matrices together without knowing what that does, because it's a very different thing than you think it would be in normal mathematics. So let's actually let's put together some something here. Let's call this, let's make a new matrix. Y equals, let's see, what are we doing? We're going to make a linearly spaced matrix using the linspace command. Remember that linspace makes a matrix of numbers between the first number that you give and the last number that you give. And it gives you the number of elements that you want in between. So we're going to do between 1 and 3, and we want 5 total elements in the matrix. So it's going to give us 5 evenly spaced numbers between 1 and 3, starting at 1 and ending at 3. And it turns out to be 1, 1.5, 2, 2.5, and 3. So there's our first matrix. And our second matrix is going to be the previous x that we used, which is x equals from 1 to 5. So there's our x matrix. We don't want it to be uppercase, we want it to be lowercase. So we remember it. Okay, so we have our x matrix, we have our y matrix, and we want to do, no, actually, sorry.
Wait, so what does that mean?
So what linspace does is it makes an evenly spaced number matrix between the first two numbers you put in. So if I put 1, 10, and I want to have 11 numbers between 1 and 10, it'll give me 11 numbers that are evenly spaced between 1 and 10. When I do 11 numbers between 1 and 10, notice that it makes it slightly smaller than 1 to fit them all in. If I do the same thing, but I only ask for 10 numbers between 1 and 10, then it just gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I do for 11 numbers, if I do 10 numbers between 0 and 10, then it makes the numbers slightly bigger than 1 to stretch them out a little bit. So it makes evenly spaced numbers every time. And I could do 11 numbers between 0 and 10, and it would give me 0 to 10, right? So no matter what, it spaces out however many numbers you want, that's the last number you put in, between the first two numbers you put in. Does that make sense? That's the linspace. Okay. I'm trying to decide what I'm going to do from what they're doing here. Let's do, so in the next problem, they're actually building a multiplication table in the next little thing that they're doing with us, and they're going to use a new function that we've not used before called mesh grid, and this is a confusing one. Just because it does something a little bit strange, but useful. So let's look at it. Let's think of what it says here. Mesh grid replicates the grid vectors xgv and ygv to produce the coordinates of a rectangular grid x, y. The grid vector xgv is replicated using this function, number of elements times, to form the columns of x, and the grid vector ygv is replicated number of element times to form the rows of y. Now that is really confusing because they're using two functions here we don't know, num element. What num element does is it tells you the number of elements in a matrix. We've used it before. So if we do number elements in x, for example, we get 5. There's 5 actual elements in the x matrix. So what does this do for us? Let's find out how many elements are in y. Num elements in y is also 5. So we've got between 1 and 5 for y, 1 and 5 for x. What is y? Well, y is this one that goes from 1 to 3 by 1.5 and 2.5. And that's fine. Okay. What just happened? Did I close the wrong thing again? Dang it. Closed the wrong thing again. I hate that. I'm closing MATLAB every time I try to close something. Anyway, so let's build our matrix. Let's build us some matrices again. Let's build x equals 1 to 5, right? In our very shortcut method. Y equals, let's do 1 to 3 just to make it a little easier on us. That's what they do in the book as well. So we've got these two matrices, and we're going to build a new matrix from these two matrices in what we call a mesh grid form. So let's see how it works. Now the reason this is confusing is because of the what's the word for this? I can't remember. But anyway, it's the formatting that we use to do this. So the formatting goes like this. We're going to create a new matrix by putting in square brackets. And we're going to name some new parts of our matrix. We're going to have a new x, and then we're going to do a comma, which means we're going to have a new row, no, a new column rather, and we're going to have a new y, new underscore y. So that names two new columns, new x and new y, new underscore x and new underscore y. And we're going to give them some values from this function we call mesh grid. And what mesh grid does is it takes two vectors that we've already got, x and y, and it can do it with matrices as well. It can be very complicated actually. But it's going to create these new matrices from these vectors. Okay? So, and these new matrices are going to be new x and new y. And these aren't actually, I misspoke, these are not actually going to be columns. They're actually going to be matrices. So let's see what happens here when we do this. So the new x becomes 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And the new y becomes 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. But notice that the 1, 2, 3, 4, 5s are in rows, and the 1, 2, 3s are in columns. So what it did is it took x and y and it said, what are the numbers of rows or elements that are in x and y? And it put the number of elements in x, and it made that many columns, 5 columns from x, because x had 5. And then rows in y, they gave us 1, 2, 3 rows. And then it actually made the columns from x, or sorry, the rows from x, 1, 2, 3, 4, 5. And it made the columns from y, 1, 2, 3, 1, 2, 3, 1, 2, 3. Right? So it's a little bit confusing, and rightly so. It's understandable why it's confusing. If we did this the other way around, let's see what would happen. Instead of x comma y, let's do y comma x. Let's change it and see what happens. Instead of having 5 rows and 3 columns, it has, or sorry, 3 rows and 5 columns, it has now these 5 rows and 3 columns. It switched it around, right?
So what exactly does
Mesh grid takes 2 matrices and creates, and in this case, we're taking 2 vectors. So we're taking 2 row vectors, right? X and Y, which X has 5 in it, 1 through 5, and Y has 1 through 3 in it. And it's saying, well, we're going to make a set of matrices now that are 5 rows by 3 columns, because X had these, well, sorry, it's not 5, 3 rows by 5 columns, because X had 5 columns in it, and Y had 3 columns in it, and they turn the X one into the number of columns and the Y one into the number of rows, and then they make a new matrix that has that dimension. Now it's a dimension of 3 by 5, where the Y determined the columns, the X determined the columns, the Y determined the rows, right? And then it put into those matrices the elements from X into the first one, into rows, and the elements from Y into columns in the next one. Okay? And it is confusing. It's weird. But the reason that they're doing this is so that they can use these to now graph things, to create. When a computer wants to, for example, when a computer wants to make a graph of a two-dimensional object, like a curve on a graph, it has to go step by step and calculate each point, right? But it doesn't just take one point from here and then calculate it, and then go to the next point and then calculate it. It actually makes two matrices like this and calculates them all at once. Because using 2 matrices like this, turning one of them and inverting one of them, you can actually do all of the points at once using matrix algebra. And if you've used matrix algebra before, you can understand how that would work. But if you haven't, then it's a little confusing. But the reason is because of matrix algebra. In matrix algebra, instead of having to calculate point by point by point by point, you could calculate all the points at once and be done. And it takes just as much time as calculating one point, doing it point by point by point by point. And if you have 1 billion points to calculate, you'd much rather it took 1 computation cycle rather than 1 billion computation cycles, right? Because 1 billion computation cycles now starts to really bog down your computer. So this is the reason that it does this: is it creates it creates these matrices that can be manipulated, can be used by the computer to make models, to make graphs of things. Now, that's not immediately obvious that it's doing that, and there are many other reasons that it can do this. There are many other uses for this besides just graphing. But this is what it does. Now, if we can actually create an interesting thing by doing some multiplication. If we can create a thing here called multiplication table, and we can actually take our first matrix, our matrix new x, right? Yeah, And we can multiply it element by element using the dot times function. Multiply each element by each element of the new y. And what does it give you? It actually shows you how these things are multiplied together. So it's like taking the top row and multiplying it by the first column. And that's exactly what MATLAB does with these things. So it would be like saying in our x direction we have these numbers, in our y direction we have these numbers. We need to multiply everything in our x direction by everything in our y direction to get some numbers. Well, it does that. This is a multiplication table that says 1 times 2, right? And let's see right here. 2 times 2 is 4, 1 times 1 is 1, 2 times 2 is 4, 2 times 3 is 6, 2 times 8 is 2 times 4 is 8, 2 times 3 is 6, 2 times 5 is 10, 3 times 5 is 15. So you can make it like a customized multiplication table that only covers the numbers you want, right? Which is exactly what graphing is. When you're graphing something in 2 dimensions, all you're doing is you're making a very customized multiplication table. You don't want 1 times 1, you don't put it in there. If you want 1 times 3.15, then you put that in there, right? And then you can create any curve that you could possibly, any function can be mapped this way. And that's the beauty of it. This, of course, is creating a function that, in this case, increases by 2, so it has a slope of 2. This one has a slope of 3. Very simple functions, but they are nevertheless functions. So anyway, that is that. Now let's actually use it to do something of some kind of interest. All right. So let's clear everything. Let's clear out the window. In this exercise 4.2, they want us to use the mesh grid function really quick to calculate. Let's see, we can calculate those are kind of boring. But they don't use mesh grid in anything else but those two. That's kind of weird. Oh, here they do. They use mesh grid in this example, so do they use it over here? Oh yeah, they do use it here too. Okay, so we'll use this one. So here we're gonna calculate the distance to the horizon depending on how high you are standing above sea level. And there is an equation for this, and it's actually an equation you're all familiar with. It's the Pythagorean theorem, just a slightly modified version of it, where you have a radius squared. Let's put this in as a comment. So you have radius squared plus d squared equals r plus h quantity squared, where h is your height above the earth, r is the radius of the earth, and d is the distance to the horizon. And what you want to do is you want to solve this equation. So when you solve this equation, because we want to know the distance, if you solve this equation, you get an equation that looks like this. D equals the square root of h squared plus 2 times r times h plus 2 times r times h. So there's our equation that we're going to need to get some answers for, some numbers for. But we want to do this in more than one place, not just on Earth, but also maybe on the moon. And we're going to do heights of mountains from 0 to 8,000 meters. That's not right. We should do it from 0 to like, the highest mountain on Mars, I think, is 24,000 meters. So let's do it from 0 to 24,000 meters. So we're going to do it, we're going to do this on Earth, and the radius, so we're going to do this on Earth, can't spell, and Mars for mountains from 0 to 24,000 meters. I'm pretty sure that that the biggest volcano on Mars is about 3 times as high as Mount. Why is it 3 times as high? Do you know? Because the gravity on Mars is much lower than the gravity on Earth. The gravity on Mars is about 3 times as low as the gravity on Earth, and so it doesn't pull the mountain down. Erosion is caused by gravity. And if your erosion is 3 times, if your gravity is 3 times lower, your mountains can be 3 times higher. So, also there's no rain on Mars, so there's not as much erosion from rain either. Rain and snow and other things. But anyway, we're going to be doing this problem here, and we want to know what the distance is. Though you can see the horizon both on Earth and on the Moon. Or both on Earth and on, is it the Earth and the Moon? I thought it was on Mars. Oh, it's the Earth and Mars. Well, whatever. Earth and the Moon, rather. There aren't very many big mountains on the Moon. Mount Maryland, I think, is the biggest one. So anyway, let's do this example. We're using this formula, but we need to input our data, right? So we're going to go ahead and we've cleared everything out. So we're going to start off with, we're going to use they're using the bank format just because it takes everything down to 2 decimal places and makes it easy. And that's fine. And then we're going to define our height vector. Height is going to equal, and we want some numbers between 0 and our highest number. Well, let's go ahead and use 8,000 like they do, since the mountains aren't that high. We're going to go between 0 and 8,000. If I go between 0 and 8,000, it's going to give me a huge, huge array. It's going to give me an array that's 1 by 8,001, because it's taking it step by step by step, one at a time. Let's take it in bigger steps. Let's do it height from 0 to 1,000 in steps of 1,000. So we do 8, we go 0 to 0, colon 1,000, colon 8,000. So our steps are by 1,000 meters at a time. So now our vector over here is only got 9. I think it's 1 by 9 double. So it's only got 9 elements in it. Makes it a little easier. And then they want to convert meters to kilometers. I don't know why they want to do that. So they're going to do that. They're going to convert meters to kilometers, which means you just take height and you divide height by 1,000. So height's now going to equal height divided by 1,000. Just makes them into single numbers, I guess. And then we have to define our 2 radiuses. Radii. Right? We have a radius. We're going to have a radius. Radius vector here now. Put the radius of the moon first, 1737, radius of the moon, and then the radius of the Earth, 6378. And that is our radius vector, radii vector. And let's see, what else do we need to put in there? We need to now put these together. So we're going to create our mesh grid now. We're going to put these together into into 2 actually, and then we'll combine them into a single. And we'll start with the radii, and then we'll do height with a capital H. So we're using radii and height for our new names, for our new matrices that we'll make with mesh grid. And then we'll use the mesh grid function, and we'll put in radii, comma, height, little h, right? Let's see what that gives us. So it gives us a radii one that has all the radius in the first column and all the radius of the Earth, radius of the moon in first column, radius of the Earth, second column. And in the height, it gives us all the heights in the first column and all the heights in the second column, or height row by row, either way. And then what we want to do is we want to combine these together in a calculation. Now in the last one, they combined them just by multiply them. And we're going to do more than that because we have more than just calculation to do. Remember our formula up here, distance equals a square root of something. So we're going to actually have to do a square root. So our distance equals square root of, what is it equal to square root of? Height squared. So we're going to take our height, and that's capital H-I-G-H-T because we're using this big thing here. And we're going to square this. We're going to square it element by element. So height period squared, right? Height dot squared. And then we're going to add this to, go away. We're going to add this to, and we don't have to do the dot with when we add matrices that are alike, we can just add them. But we're going to add this to 2 times, and we don't have to use the dot times here because we're just multiplying by 2. 2 times the height, but when we multiply by the radius, we do need to use the dot times because we're multiplying two matrices together. So 2 times the height with the capital H, I-T. Sorry, not height, by radii. Oh shoot, I renamed it radii with cap radii. There we go. I used a little r for my radii there, but that's okay. So this supposedly is going to do all this math using the matrices, and it actually does. So what's going on here in our first? What do we have in our first column, and what do we have in our second column? Let's see. The first column is going to be how far you can see on the moon, because that's the first column is relating to the smaller radius. So this is how far you can see on the moon when you're at 1,000 feet. And this is how far you can see on Earth when you're at 1,000 feet. And that's in kilometers. It's because remember we converted to kilometers. So you can see 58 kilometers if you're at 1,000 feet. You can see 112 kilometers if you're at 1,000 feet on the Earth. Okay? At 2,000 feet, 83 kilometers. At 2,000 feet, 159 kilometers on the Earth. Okay? So let's see if that's actually true. At 1,000 feet above, this is actually not 1,000 feet, this is 1,000 meters. So it's like 3,300 feet-ish. So at 3,000 feet, which I have been in an airplane just over North Platte, at 3,000 feet, 112 kilometers, which is approximately, what is 112 kilometers? It's like 70 miles. On a clear day at 3,000 feet, you can probably see 70 miles. It's pretty close. So, not bad. So it does it. Hooray for us. So this is actually kind of it's kind of a very clean way to make tables of numbers that are related to each other by doing math. But using MeshGrid, it requires you to be very careful in using it properly. Otherwise, it doesn't work the way it should because you're doing math with matrices.
Does it matter if it's like capitalized? Because I see like in the book they have like stuff capitalized, and like when I'm height is capitalized.
So that has to do with how they named it. When I went back and renamed my matrices with MeshGrid, I renamed it with little r here. See that? So I just accidentally renamed mine with little r. They named theirs with big R. So it's just what you name it as. So that's the only difference. They named theirs with a big R. I accidentally just renamed mine. So they in their workspace, they would have a big R over here, a big R radii vector and a small r radii. But I ended up with just the one because I renamed it on accident. So that's a better way to do it, is to keep your variables with different names. So use capital letters when you rename it, so that you have both of them, so that you can use both of them later. But I can't use both of them later because I renamed it. So that's my fault. But good question. Okay. Let's see, we've got time to do another example. Let's do another example. Woo! This next example has a lot of numbers to enter in. I don't know if I want to enter in all those numbers. I guess it's not that many. All right, let's do it. So the next part we're going to use mesh grid again. We're going to calculate, let's see here. We're calculating the distance that a free-falling body has traveled, neglecting air friction, when a satellite orbits a planet. So we're just here, we're calculating value constant G. We want to find the distance traveled by a freely falling object on planets with different gravities. So at different times. So from time 1 to 100 seconds on different planets with different gravitational pulls. We're going to do it by 10 seconds, it looks like. So if you're on Mars, for example, or Jupiter or whatever else, the distance that you fall when you are dropped in a certain amount of time depends on how much gravitational pull there is, right? And so that's what we're going to be doing here. We're going to calculate how far things fall in time. Now this is kind of goofy because they're talking about a space shuttle, but the space shuttle does not fall with that constant when it's that far away from the Earth. Because the space shuttle travels very far away from the Earth. The gravitational pull out there is much lower than close to the Earth. So this is talking about if you're close to the planet's surface, if you're like standing on the surface or in a top of a mountain on the surface, and you throw something off a cliff, that's, you have to be pretty close to the surface for this problem to be true. But still, that's okay. So let's clear everything up again and start over. And let's start off with what we're doing here. So let's talk about this. We're talking about free fall distances on different planets when falling between 1 and 100 seconds time.
Mr. David,
Yep.
before I go,
Yep.
Jenny wanted to ask you from physics. Jenny?
What's that?
Jenny from physics.
Yes.
From physics class, she wanted to ask you if you could do her lab on Friday, make it on Friday.
I don't know about Friday, but maybe next week I'll talk to her. So. All right, so back to this problem. Free fall distances on different planets when falling between 1 and 100 seconds is the problem. That's the thing that we're trying to solve for. So the things that we have to put into this problem have to do with this equation. The equation is distance fallen equals 1/2, we'll do 0.5, 0.5 times g times t squared, where we're going to know the time and we're going to know g is going to be given to us and we're going to calculate d, right? So the things that we have to enter in include our time and our g. G and t are the things that we have to put in. So let's go ahead and start putting those things in. Let's start with g. So they give us a chart of g's. We're going to just call it g, right? And we just have to enter in all these numbers. We just have to enter in them one at a time, which is fine. So what I'm going to do is I'm going to open up just a blank matrix here. Now I'm going to open it here. I'm going to enter in all of my vectors, now all of my numbers. Now let's see here how do they do it this way? Where do they enter in G? G equals acceleration due to gravity. Wait, they're only doing two of them, 3.3 and 8.87. They're only doing Mercury and Venus. We're going to do all of them. Now they're only doing Mercury and Venus. They're kind of cheating, I think. So I'm going to put them in anyway, 3.7. I'm going to click in here. 3.7 is the first one. Good night. I can't type. Save my life. So 3.7. And then I'm just going to go to the next one, which is 8.87. 8.87. Then I'm going to go to the next one, which is 9.8. That's us. And then 1.6. And then Mars, which is 3.7, about a third of ours. And then the next one is 23.12. That's kind of a big one. 8.96. Saturn is not all that dense. Uranus 8.69. Neptune 11. And yay, they included Pluto. Pluto's still a planet. Hooray for us. And then we'll just we'll just close this out and we'll have our matrix with all of these different accelerations. If you're going to do two, you might as well do all of them, right? Because once you've entered in those things once, it's pretty easy to go from there. So we're doing that. We're calling, dang it, did I close I closed MATLAB again. Son of a gun. Why is it that I always close MATLAB? The buttons are too close together. It means I have to enter all those in again. Arrgh. Okay, let's try this again. I'm not going to type in all that other stuff. Let's just type in little g. Let's type in little g equals this guy. Let's open this up. Now when this opens, let's see what it does. Where's the close for this thing? Oh, it's over here. I keep closing this one. I need to close this one. That's my bad. Okay, I'll try to remember that. 3.7 for the first one. Click in there. 3.7 is my first one. My second one is 8.87. My third one is 9.8. And then 1.6. And that's the moon, 3.7. And then Jupiter is 23.12. 8.96. 8.69. And 11. And 0.58. Okay. Now I close it over here. There we go. And I've got my G now. Now if I type in G here, it should show me all those numbers. All those columns. Okay, good. Then the next thing we want to put in is our numbers between 1 and 100. And they're going to do it by tens, and that's fine. Let's do it by tens as well. So our numbers by tens are going to be our height, h. No, those are our times, times t rather. So time equal to t equals 0, semicolon. We're going to go by tens, or colon, not semicolon. We're going to go to 100, and that's going to be my time. So I've got that one. And then I'm going to do my mesh grid, right? So instead of little g and little t, I'm going to use big G and big T, because I'm going to change those so that I keep the old ones. I don't reassign them. And I'm going to build these vectors from the mesh grid, or these matrices from the mesh grid function, using little g and little t. And there are my mesh grid things. They're kind of big, so it gets kind of messy. But there's my big G and my big T. The next thing I need to do now is calculate using my formula. My formula says that the distance that I fall is equal to 1/2, so 0.5, times G, and it's a dot. Well, you don't have to use dot times because we're just multiplying by 0.5. So just 0.5 times G, and then I have to use the dot times because I'm going to be multiplying by T, and I'm going to be squaring T. So I need to dot times the square, or dot square it. Goodness gracious. And then I do the math. And there we have it. And it's a fairly big mess because for every planet you have all these different distances that you fall from 0 to 100 seconds. And this is measured in, let's see, it can't be right. Oh yeah, it can, because it's multiplied by 1 times 10 to the 5. So each one of these is multiplied by 1 times 10 to the 5. So you have to move your decimal point over 5 places. So this first one, which is Mercury, the distance that something would fall, move this decimal point 1, 2, 3, 4, 5 over. In the first second would be 190, I guess it's 190 meters, is that right? That seems really far. Let's see, where's Earth? Earth is right here. For the first, no, it's not the first second. That's the 10th second, right? Because we went by tens. So after 10 seconds on Mercury, it falls 190 meters. After 10 seconds on Earth, something falls 490 meters. And that makes more sense, much more sense. Something that falls 10 seconds does fall a long, long way. So, anyway, that is it. So, that takes us to the very last section of this chapter. We should have done format bank again. Let's do format bank, because then that will give us the right numbers without the scientific thing. And let's look at distance. So there are the numbers properly. And then if we go look at, if we open up distance, we can see them properly. It's 185 meters for the 10th second on Mercury. For the 10th second on Earth, it's 443 meters. Or sorry, on Earth it's 490 meters. On Venus, it's 443. But on Mars, it only falls 80. On the Moon, it falls only 80 meters. And on Mars, it only falls 185 meters. And that's because the acceleration is so much less on Mars and on the Moon. It's not that things just don't accelerate on the Moon and on Mars very quickly. So if you drop a rock off of Mount, it's the same mountain that's in Greece. It's called Mount, anyway, whatever the big mountain is on Mars. It takes forever for it to speed up compared to on Earth. And that's why things on Mars can grow higher, because things just don't get pulled as hard down. So that mountain is 3 times higher, even though Mars is about the same size as Earth. Mars doesn't have the density of Earth. Anyway, so there it is, the mesh grid, using the mesh grid to do some simple matrix mathematics. Okay, now we're done doing math with matrices. We're going to now just learn how to build some special matrices. It's pretty straightforward stuff, not very difficult to do, but it can be useful. So the first one is a matrix of zeros. So if you do a matrix of zeros and you do 9, it'll build you a matrix of 9 by 9 of zeros. Let's do another one that's smaller so you can see it a little bit better. A matrix of zeros 3, you get a matrix 3 by 3 of zeros. 0, 0, 0, 0, 0, 0. And if you want to make a matrix of zeros that is 3 by 5, you just do 3 comma 5. 3 rows by 5 columns of zeros. And this can be useful because a matrix of zeros can be useful in many ways. But there's also a matrix of ones used the same way. A matrix of ones that is 2 by 7, or a matrix of ones that is 7 by 2, or a matrix of ones that is just 4. We'll give you a 4 by 4 matrix of ones. Pretty simple stuff. And then there's a diagonal matrix. Those of you who have done a little bit of matrix algebra would understand the value of this. A diagonal matrix of 5 Did I do that right? Oh, I did it wrong. I used the function wrong. If I already have a matrix, see what matrices do I have here? Let's make a matrix. Let's call it matrix. And let's put a bunch of numbers in it. Let's put just a bunch of random numbers, except along the diagonal. Along the diagonal, I'm going to put the numbers 1, 2, 3, 4, and 5. And everywhere else, I'm going to put just some, I'm just going to enter in some random numbers. So there's my matrix. I'll close it over here so I don't close the whole thing. And I've got this matrix now that's got all these funky numbers except on its diagonal. The diagonal starts at 1, 1 and goes to 2, 2, then 3, 3, then 4, 4, then 5, 5, row and column. And then I asked for the diagonal of my matrix. If I ask for the diagonal of my matrix, it gives me a column that has all the numbers that are on the diagonal of that matrix. And if I ask for the diagonal of another matrix that does not have a diagonal, so for example, if I ask for the diagonal of T, it did give me that. Why did it give me that? Does this have a diagonal? Apparently it does. Oh, so if I ask for the one, oh, this one is not a square matrix. It's an 11 by 10 matrix. But what it will do is it will give me the diagonal anyway. Starting up here, it will go down to here, then to here, then to here, then to here, then to here, and here, and here, and here, and here. But it ends up just ending right there. So it will give me the diagonal of a non-square matrix as well. So that is how that works. Then I can use this function as well to create a diagonal matrix. So if I can create a diagonal matrix like this, where there's only things on the diagonal, it turns out. So I'm going to say that A equals, so diagonal equals, I'm going to tell this matrix what the diagonal is going to be, in other words. So I'm going to say it's going to be, let's just do what we did before. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's my diagonal, and it just makes this little row vector, right? And then if I tell, if I use diagonal, the function, and then I put in my little thing here, diagonal, what this will do is it will create, I believe it's going to create, a diagonal matrix with those things on the diagonal. So let's go to, and that came out as the answer, so let's look at the answer here. And look, it's a 9 by 9 matrix with 1, 2, 3, 4, 5, 6, 7, 8, 9 on the diagonal. And everywhere else it just fills in with zeros. So there's the diagonal function building a matrix that is purely diagonal with zeros everywhere else. And then, let's see, we can flip matrices around. So let's look at our matrix. Let's build a new matrix here. Let's build a new matrix. M equals 1, 2, 3, 1, 2, 3, 4, 5. And then let's do let's do 2, 3, 4, 5, 6. And let's do 4, 5, 6, 7, 8. And then there's our matrix right there. So we have our matrix that is 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8. And I want to do this. I'm going to flip R, which means I'm going to flip it from right to left. Flip. Did I do it right? Flip LR. Flip LR. It should do it. Oh, no, I didn't. I did it wrong. I left out the L, so it's flip LR. There we go. And what it does is it turns everything around from left to right. So instead of starting with 1 and going to 5, it starts from 5 goes to 1. Instead of going from 2 to 6, it goes from 6 to 2. And then from 4 to 8, it goes from 8 to 4. And I can also do the flip, excuse me, up and down. So flip up D, UD here. Do that with our M matrix, and it'll flip everything from up to down, give us the mirror image up and down. Okay, so there are some other things you can do with matrices. And then the last one is the magic matrix. What is the magic matrix? So magic matrix, we'll start off with a magic matrix of 3. A magic matrix of 3. See if I can remember how this goes. Something to do with adding them together. It's an ancient mathematical thing. Let's see, here we go. The sums of the columns are the same as are the sums of the rows. Okay, so if you add all the columns together, they're the same, and if you add all the rows together, they're the same. So 8 plus 3 is 11 plus 4 is 15, and 8 plus 1 is 9 plus 6 is 15, right? And 3 plus 5 is 8 plus 7 is 15, 4 plus 9 is 13 plus 2 is 15, and 1 plus 5 is 6 plus 9 is 15. So you always get 15 with this magic matrix. And if I do another one, if I do another magic 3 matrix here, it gives me that one, but if I do a magic 4, it's different. 16 plus 5, 21 plus 9, 30 plus 4, 34. Going across this way, 16 plus 2 is 18, plus 3 is 21, plus 13 is 34. And it works either way. Now, does this have any practical purpose? Absolutely not. As far as we know, there's nothing useful about them, but they're interesting. And MATLAB has an algorithm for building them. So if we ever do figure out a reason for them, MATLAB will be able to do great things. And that is the last of the chapter for today. So today we learned mostly about using MeshGrid to do a little bit of simple matrix math and to create some values of some tables of numbers essentially. And we'll do some of that in the homework. But then also creating some matrices, some simple special matrices. We did some of that today. Beyond that, we're pretty much done. Next time, we will get into using those tools to now plot things. So we're actually going to get into making graphs, making imagery, making animations, get into the more exciting stuff, hopefully. It'll be more interesting. Chapter 5, I believe we take 2 weeks to do because it's a lot more involved. And then chapter 6, we'll be doing, I believe, more of the same. No, chapter 6, we're going to go into creating some files to do similar things. So anyway, we will be doing more of the same. We'll just be doing it in a slightly different way. So we're done for today. We're done for this week. Remember to get in, work on, remember to enter in your notes for this week. Get in and work on the entering in some tips and tricks into the shared document, and then do the homework assignment. And we will see you next Monday.